Hello, my name is Samantha, and welcome back to another Embedded Systems workshop. This will be our first of the summer, so we'll be covering electronics theory, then going over some concepts we learned in the spring workshops. Let's get started.
All right. So welcome to Embedded Systems Workshop. Today, we're going to be covering more of the electronics theory and just review some of the parts we've gone over in the previous workshops. So, overview today, we're going to learn about a lot more theory behind direct current circuits, which is the circuits that we're working with when we work with Arduino. We're going to learn about some of these circuit elements. And then lastly, we're going to review components that we learned previously, like buttons, LCD screens, and the servo, mostly the LEDs. So starting off, a basic DC circuit simply comprises a power source and a load. In this first example here, we have the power source, which probably is a battery. Current flows into the load, which in this case is just a resistor. Often current flows out of the positive terminal of the power source into the load, which in this case is just a resistor, and then back into the negative power terminal of the power source, which is why this is called a circuit, because it completes a loop. And we have another example with a battery, a resistor, and a small LED back into the negative terminal. A little bit of terminology to note. These three terms are going to be the most important: voltage, resistance, and current. So voltage is simply what we call potential difference between 2 points on a circuit, and that's measured in volts. If you've ever heard like a 5-volt battery, you ever wonder what that means? Well, this is what it means. It means there are 5 volts of potential difference between the positive and negative terminals. Resistance is simply the electrical resistance that's applied to the circuit, and that's measured in ohms. And then current is the flow of charge for the circuit, which is measured in amps. And 1 amp of current is equal to 1 coulomb of charge per second. I can get into what a coulomb is another time, but for purposes of 1 coulomb is a unit of charge. And then the variables that we're using for these are V for voltage, R for resistance, and I for current. Here's a few basic circuit elements put together. We have the battery that supplies its power, it's applying voltage currently. Then we have a switch, which is simply an on-off device. When you close the switch, or like say turn it on, that completes the circuit. But when you have the switch open, there's a break in the circuit and current can't flow. Close the switch, that completes the circuit. We have a load. That's simply whatever applies resistance to the circuit. That can be resistor, light bulb, a motor, an electrical heater, what have you. Then we have a couple of other things that might come in handy later on. We have a voltmeter and ammeter. These are used to measure voltage and current in the circuit. A voltmeter simply measures the potential difference between 2 points. An ammeter simply measures the current. Just a few basic elements, like the power source. And by the way, on each of the slides for the basic circuit elements, there's also going to be the symbol, that represents it on a wire diagram. The power source here, it simply provides the voltage that allows electricity to flow. I'm sure you're all familiar with batteries. And that's a common example of power source, and it's represented on a wire diagram by this symbol. Sometimes you'll see only 2 sets of the big line, small line. Sometimes you'll only see 2, sometimes you'll see 3, but the symbol more or less looks like this. Here's a resistor. We all know about these. We've used these before. Resistors simply slow electric current. It's measured in ohms. And the resistors we use, the resistance is measured by colored stripes on its body. And each stripe has a different value. And each stripe has a different value depending on the color and its location. And a resistor is represented in a wire diagram by this jagged line here. And then it'll usually have the resistance value on top, either on top or on bottom. potentiometer is just a variable resistor. You can change how much resistance is applied by twisting the knob. This is useful if you're trying to adjust brightness, say the brightness of a light, and to adjust the power of, let's say, a motor or what have you. And it's represented by that same jagged line, but with an arrow going into it. Except we have a capacitor, which is an element that stores charge similar to a battery. The main strength of a capacitor is simply its ability to rapidly charge and discharge, which makes them useful as a buffer between power source like a battery and a load, particularly one with varying power requirements, because a battery has a limit to how fast it can discharge current. Well, a capacitor has a much higher discharge rate. So for the same voltage, it can supply much more current. The capacitor's ability to store charge is measured in a unit called farad, with 1 farad equal to 1 coulomb of charge per volt of potential difference. For example, the capacitor in this image is 100 microfarads, which means for 1 volt of potential difference, we'll be storing 100 microcoulombs, which is how I believe 100 millionths of a coulomb, and it's represented on a circuit by these 2 vertical lines of same length. And here's something important. I always talk about you have to connect something to ground. Well, here's why. The electrical ground is the reference voltage for the circuit. Basically, you can consider the ground to be 0 volts, and then everything else in the circuit is calculated with that being 0 volts. And it's represented on a circuit with this symbol, usually 3 or 4 lines of decreasing size, and it only goes into one area. You don't have one input. You don't have an in and out. You only have an in. In practice, there's many ways to do an electrical ground. For example, you can see in this picture, there's a wire connected to a spike that's then driven into the ground. That is actually where the term ground comes from, because the ground was just a physical connection to the earth. In other cases, it's simply the negative terminal on a battery, or simply a return path for the current. All you need to know is that the ground is, on a circuit, the ground is 0 volts. And then here's the ground and power on Arduino as an example. The red wire connects to a 5-volt pin, which is power. There's also a 3.3-volt pin for certain electronics that use 3.3 volts instead of 5 volts. Then the black wire here connects to ground, and there are a total of 3 ground pins. There's 2 next to the there's 2 next to the 5 volts, and there's one at the, from this perspective, top right next to the pin 13. Any questions so far before I move on real quick? No questions so far? Oh. All right. Let's move on then. Now we get into the fun stuff, equations. So the most basic in a circuit is called Ohm's law. Remember ohms, which is the value of resistance. This is the guy who developed that, a guy by the last name Ohm. So Ohm's law says that the current through a circuit in amps is equal to the voltage in volts divided by the resistance of the circuit in ohms. And how that's expressed is I equals V over R. And you can rewrite this too. If you want to get the voltage given resistance and current. You would simply rewrite this as V equals I times R, or voltage equals current times resistance. Or if you wanted to get the resistance, you could do R equals I over V. the power of the circuit is equal to the current times the potential difference, or essentially I times V. And using some of these equations from using the equation from Ohm's law, you can also rewrite power as I squared R, or current squared times resistance, or V squared over R, or voltage squared over resistance. Then capacitance, you remember the capacitors? The charge on a capacitor is equal to the capacitance times its voltage, or Q equals C times V. The C being the capacitance. For example, to have 1 coulomb of charge would be 1 farad times 1 volt. 1 volt of potential difference. All right, now we have a couple of exercises, and I'm going to give you guys a bit of time to work on these. So 5 amps of current passes through a 10 ohm resistor. So what would be the voltage drop across this resistor? Second question is, a particular light bulb will blow if it receives more than 20 milliamps of current, with a milliamp being 1,000th of an amp. With a voltage of 5 volts, what's the smallest resistor that we can use with the LED and not blow it out? Then the third question is, we have a 10-volt battery supplying 2 amps of current to a motor. How much power does the motor use? I'm going to give you a bit of time to figure out these questions. Oh, yeah. Is it? Oh, yeah. Yeah, there is a whiteboard here. Okay. Yeah. 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 Mhm. And this is editable by everyone, right?
Yeah, it should be.
All right, let me put down a sticky note. Just test it out. Okay, let me just test that. All right, let me just delete that. All right.
If you guys just want to put a sticky note on.
If you want to put a sticky note on here that just says your answer, you can do that.
I added some of the equation.
Relative, yes, yes, so added some of the relative equations.
You need them.
Yeah. You also add in
Stefan, do you maybe want to walk through the first one?
Yeah, give me 1 second to just. All right, so yeah, I can walk through the first one if people have trouble with it. This is pretty easy. As we can see, we have the equation, one of the equations from earlier, which is V equals IR, which is simply I equals V over R rewritten. So if we want to find V voltage, take I. Let's see, V equals, it was 5 amps. 5 amps times 10 ohms. Or does it look like a 6? Let me erase that. Does it look like a 6? Times 10 ohms. And that means we get a V of 50 volts. Make sense?
Yeah. So we've
All
got
right.
5 amps of current, which is I. And then we've got
10 ohms of resistance, or 5 amps times 10 ohms gets us 50 volts. Second question here is the light bulb will blow if it receives more than 20 milliamps of current. So I equals 0.02 amps equals 5 volts over some R. And then if we rearrange the equation, we can rearrange this equation to get R equals 5 volts over 0.02 amps. That has to be R. That means R equals, actually, it means R has to be, actually, no, yeah. Let me actually show one thing. So this should actually, so here we go. What this means that, so I can actually rewrite it is, no, actually it has to, yeah. Means this part here has to be less than, or 0.2 amps, which means if we rearrange this equation, if we rearrange the equation, we get R is greater than or equal to 5 volts over 0.2 amps, which means R is greater than or equal to 250 ohms. That makes sense? Okay. Now, next question, question 3. Question 3 is that we have that 10-volt battery supplying 2 amps of current to a motor. So how much power does that motor use? Well, we have the current, we have the voltage. To get power, P equals IV. P equals, it's 2 amps times 10 volts. means P simply equals 20 watts.
That's pretty simple.
Simple enough. All right.
Does anyone have any questions about these three problems?
If you have any questions, feel free to type in the chat.
Okay. You can probably go on to the next part
Next slide.
because there's a couple more exercises.
Yeah, there's a few more
There's
exercises
stuff in
later on.
Tinkercad.
All right. Okay. Next thing that's important we got to talk about is series and parallel. So two or more circuit elements are in parallel. They allow a current to take more than one path. For example, we have this parallel circuit of three capacitors in parallel. Then series, so a bunch of circuit elements are in series if the current can only flow in one path. Like this demo series circuit, which is simply three capacitors lined up one after the other. These three capacitors are in series. And that depending on if they are in series and parallel, the equivalent resistance, the equivalent resistance, as we call it, of a group of resistors is going to change. For in series, you simply add the resistances of the three up. So we call R equivalent or equivalent resistance simply equal to the sum of the resistances of the resistors in series. In parallel, things get a little bit trickier. So we have, for example, R1 over R equivalent is equal to 1 over R. The 1 plus 1 over R2 plus 1 over R3, and so on. And I need to fix something on here. This is actually 1 over Rn, as it just goes on. So basically take 1 over each group, 1 over resistance of each resistor, add them together, and take 1 over that, essentially. And for capacitors, if we're talking about equivalent capacitance, the reverse applies. Capacitors in series are going to follow what resistors do in parallel. Capacitors in parallel are going to follow what resistors do in series. For example, if you have capacitors in parallel, you simply add up their capacitances to get the equivalent capacitance. Whereas if you have three capacitors in series, you do this equation with their capacitance. You do the resistor parallel equation for their capacitances, get the equivalent capacitance. Here's a short exercise. We have a couple of groups of resistors. Calculate the equivalent resistance of each of these two groups of resistors. So you're going to need two answers for this one.
All right, the Jamboard's set up for the next exercises. So if you want to type in chat or if you want to draw directly on Jamboard, that can work. We're going to start on slide 4.
If anybody has any questions about any of the problems, just feel free to just speak up. All right. All right. Okay, we have, so you guys got the first circuit correct, 45 ohms. The second one is close. There's one thing you forgot to do. Something you guys forgot to do. Remember, it's 1 over R, R equivalent, is equal to 1 over R. 1 over R, and so on, and so forth. So yeah, so the equivalent resistance of this circuit will actually be 8 over 7 ohms. You gotta remember to do the 1 over it. You gotta do it almost all the way there. You gotta remember that it's 1 over R equivalent. It's 1 over the R equivalent when you add them. So once you add all three of these together, then take 1 over that number. All right, next exercise. The fifth one is a little bit more complex because we have a circuit we have a resistor in series with a pair of parallel resistors. So calculate the current I through the circuit. And here's a quick tip. If you want to find the resistance of something like this, first find the equivalent resistance of this. Find the equivalent resistance of this, and find the equivalent resistance, and then add up the two resistances to find the equivalent resistance. Erase this. Yeah. All right, so you were correct in finding the equivalent resistance. Wait, why is it this erasing? Oh, yeah, you were correct in finding the equivalent resistance of this part of the circuit over there. But you forgot about this 5 ohm resistor. There you go. Yeah, there we have it. It is 4 amps of current. The trick here is find the equivalent resistance of this portion. The trick here is find the equivalent resistance of this portion, the parallel portion, then treat it as a single resistor, and then add it in series with the 5 ohm resistor.
Cool. Are you ready to go on to the next one?
All right, next exercise. Next exercise is what's the equivalent resistance of this circuit here? And then explain your answer. I'm just going to say for this portion, just ignore this portion. Only find the equivalent resistance. Just ignore the battery. Trust me, it's not a trick question. Here's a crucial thing you guys are forgetting about, and that's this wire. I see you. All right, you guys are catching on now. Good. Is anybody able to? Anyone here want to explain? Want to explain their answer? Despite the fact we have 10 ohm resistor here and then another 10 ohm resistor, why is the equivalent resistance 10 ohms and not 20? You want to put your type out your explanation in a text box or put it in the chat. All right, close, but we only have one resistor. You say there's two resistors in parallel. They do have zero resistance, and so this part right here has zero resistance, but why does it have zero resistance? So, all right, so the resistor in parallel with the wire has zero resistance, and we just change the pen color. So what do we call this portion? What do we call it? Oh, why am I doing that? Why am I writing a question mark? Why am I writing it? So let's do a question mark. So what do we call this? Not a load. You guys give up yet? You guys give up yet? All right. Here's the answer.
We talked about it, so it might be good to
explain. Here's the answer. This is what we call a short circuit. And I'm going to demonstrate later on. I'm going to demonstrate in a little bit why this can be dangerous. And it's good that you guys caught on to the fact that there's a wire here that in this resistor. That when you have a short circuit in a circuit, when you have a short circuit, it'll ignore this entire portion here. Why am I drawing that in blue? Yeah, so when we have this short circuit, resistor here is effectively ignored in our calculations. I think you guys managed to caught on to the fact that we have a short in here.
Another thing to note is that current will take the path of least resistance. So that's why we have the short there. It'll just follow the wire.
Yeah, in this case, the majority of current is going to take the path of least resistance. Some current is going to split off and take the higher resistance path. But when we have no resistance here, that creates our electrical short. All right. And here's the solutions. Here's a few demonstrations, actually. I'm going to be using Tinkercad for these demos. Try any of these yourself. You might need to create an account, which is easy enough to make. Just sign in with your Google email. It's going to demonstrate each of the components that were discussed previously. Parallel series and circuits in series and parallel, resistors in series and parallel, and then things to avoid doing like our short circuit, and then swap power ground, etc. So first I'm going to demonstrate our little series and parallel demonstration, actually. First things first, just going to go onto Tinkercad, create a brand new circuit. Going to load in this breadboard. This battery here, why am I using a 9 volt is entire. I'm just going to use a 3-volt battery for this. What's cool is here, you can add wires, like so. I'm going to do positive to positive, negative to ground. I'm going to recolor these wires so I can more easily identify them. Perfect. All right. We have this resistor. I'm just going to put this resistor here. I'm going to give this a value of, let's say, 330 ohms, because we've used that before. I'm going to put this completely random little light bulb here. And I think we'll give it a nice yellow color. And lastly, also, why do I have this connected to power and it ran out of power? Lastly, just have a wire connect that to ground. And then color that black. Start simulation, the light turns on. This is how we made a little basic circuit. Start simulation. There. We also have this potentiometer here. Is there a way to turn the knob? All right. There's a way to turn the knob. That's good. Now, I need to demonstrate here. How do we use this potentiometer? Let's put it in there. We'll color that red. And ground will be colored black. And this third wire goes into our light. Actually, I'm going to add just a resistor there so I don't blow up. Rotate you around. Put this guy here. This wire can go. The LED here. Put the LED there, then this goes to ground. If I start the simulation, I can turn up the brightness. I can adjust the potentiometer and turn up the brightness of this LED. If I stop it, I can also, let's just lower the resistance to about 20. We can get a brighter LED, in theory. Just ramp up the resistance, actually. I can actually just, there we go. Now we have an adjustable light brightness.
If you want to, feel free to follow along in Tinkercad.
Yeah, you can follow along in your own Tinkercad circuit. Yeah.
Mm-hmm.
We do have a capacitor. The capacitor is going to be used in some things, but I'd say really for the purpose of, okay, actually, you know what? I can show you guys here. Just grab a multimeter. I can show you guys what happens with the capacitor. Let's grab another breadboard. Measure the amperage here. Actually, I'm going to measure the voltage. Pull out a little capacitor. Actually, where is it? Pull this polarized capacitor, put that in here. Voltage, let's rate it for 16 volts. Pull this battery here. Then here, I'm going to use this here. I'm going to demonstrate how a capacitor gets charged and discharged. When we charge this capacitor, all right, this is this is a voltmeter. If I start this, okay, maybe having a resistor would help you guys actually visualize this. Yeah, maybe I think I need more resistance actually. And you can see that the voltage gradually picks up as current is charging the capacitor. And it's gonna start to slow down as it gets to 9 volts, as it charges up to its full 9 volts. Well, it's not even actually gonna reach 9 volts. Let's see. Give it enough time and it probably will. So I input a very high resistance value so you could sort of visualize it. And then if I put a motor, let's just put a motor here. Let's run in here. I'm going to install this little switch here. All right. Okay, something's not going right. Mm-hmm. Oh, that's why. Here we go. I actually can probably, yeah, let's slow this guy down actually. Oh, I see the issue. Stop simulation. Just need to move this guy over. This here, not here. I could probably demonstrate a capacitor here. So this is why is that capacitor not charging? Actually, I could probably just lower that. I think, in theory. Actually, I'm definitely doing something wrong here. But anyways, what a capacitor is meant to do is just store charge. You could see from my previous demo that the charge would simply ramp up. So we got closer and closer to its full potential difference. And if additional current was needed, the capacitor would be able to quickly charge and discharge. Now I want to demonstrate a few things Like here we have series and parallel. Got a 9-volt battery. We have a couple of ammeters here, ammeters which measure the current. So first here we have 2 resistors, all of these here, 10 ohms. We have another 2, which are also 10 ohms. Different here, this first circuit, this top circuit is in series, bottom circuit is in parallel. If I start the simulation, you can see the difference in amps. You can see the difference in amperage here. Because this is what's going on here, this is effectively 20 ohms resistance. Well, this here is effectively 5 ohms. So we have about 4 times the current flowing through the top, through the bottom one as the top one. Do that difference in resistance. And now here's something else. Here's one of those things that you just want to avoid. So you remember earlier that short circuit demo, right? You start this, the light bulb turns on. We have so we have this power, so we have our power, goes through the resistor, that turns on the light, or flows back to ground. Simple enough. But what if I add this little wire here? This wire will short circuit the system. If I start simulation, the LED blows. So this is what can make a short circuit dangerous, especially with something that is high voltage, depends on high voltage, low current to run. And then if you short it, that's probably gonna, let's say if you short circuit with a motor, the motor's probably gonna receive a surge of current, probably gonna spin so fast, extremely fast, and probably tear itself apart, which is not something you wanna have happen, especially not something you wanna have in, let's say, a car, where a motor would just tear itself apart. To get rid of the short circuit, we have, and you can see the LED is now completely fine thanks to the magic of Tinkercad. If I delete that wire, everything goes back to normal. If I add the wire back in, we fry the LED. I can also demonstrate what happens with this DC motor. I'm gonna move this lamp and move the LED out of the way real quick. And demonstrate what happens with just this motor. Spinning at around 10,000 RPM. It's spinning at around 1,000 RPM with this resistor. And if I short circuit this thing, we get 17 times that. So you can see why you want to avoid a short circuit. 1,700 RPM is probably going to be enough to make the motor tear itself to pieces. And that is, you can see why we want to avoid a short circuit whenever possible. Now, there are some systems out there that take advantage of a short circuit, but for our purposes, it's something we want to avoid. Next, another one I want to show here is what happens. Let's delete this motor real quick. Put this light back in. What happens if we flip the power and we flip the ground? See, so this used to be where power would go in. Light bulbs are one directional, which means the positive end has to be connected to the anode, which is our power in, has to be connected to positive, and the cathode, or negative end, has to be connected to ground. Here, what I've done is I've flipped that. If I run this, the LED doesn't turn on because it needs the power coming at the anode and not the cathode. Now, with other things, it does make sense to flip direction. Well, let's just put these guys back for how they would normally. Put that there, put that there, and this around. Start this. It's turning counterclockwise here. What if then what I'm going to do is flip them. And now it's turning clockwise. With a motor is one of the things you can flip power and ground. What's going to happen is it's going to turn in the opposite direction. And this is how an electric car achieves reverse. It just simply flips the direction the current is going, essentially. Now, most electric cars use alternating current, not direct current like this. But for a smaller vehicle, this is how you can achieve directional control. And for a smaller like car you build here, you can achieve directional control using this. But for other things, let's see, is there something I can blow up in here? Let's see, good. I'm pretty sure there's something here I can use. Anyways, you just want to, well, anyways, there's let's see if there's a sensor in here. I'm pretty sure I can blow up a sensor by, yeah, here we go. Let's put this ultrasonic distance sensor here. VCC goes to power. This goes to ground. And if I flip it, oh, well, there's a little connection to power. Okay. All right, that's how it normally would be. If I flip the two, okay, it's not. It doesn't. This one doesn't demonstrate it. This one doesn't demonstrate it, but yeah, this is not something that demonstrates it. But just in general, keep the power and keep the positive going to positive and the negative going to your ground. Unless there's a situation where you can get away with it, like this motor, where it can actually be helpful to swap power and ground. Okay. And that is what. Oh yeah, one more thing I want to demonstrate is what happens if we have some light bulbs here. Let's grab some LEDs. Grab a few more LEDs. What I'm going to do is place these guys in series, and I can demonstrate something. Nope. Yeah, here. So place these guys in series. Just want to rearrange these wires real quick. It's supposed to go in there. And this should come up to here. Let's put these guys in series. They all light up. And let's say I remove one of the bulbs. Nothing happens. So then, what if I put these three in parallel? With the magic of Tinkercad, I could rearrange these wires. Then we can put all three of these in parallel. Stop generating the new wire. All three of these in parallel. Okay, it's around. See all three light up. And if I can remove the light bulb, the other two aren't affected. So this is one advantage of a parallel circuit. If say one of these lights goes dead, the other two aren't going to be affected, whereas they would be if they were all in series. This is why you often see like lighting strips. Most lighting strips are done in parallel rather than in series. So that if, let's say, one light fails, the entire strip doesn't go dead. Okay. I have a couple of slides for those who aren't here or some reviewing it. So, any questions on the demonstrations before we go into the review of some of these stuff we've done previously? Yes, Tinkercad is quite cool. One can do with what Tinkercad can allow you to do is model a circuit like an actual physical circuit. Upload your code to the virtual Arduino and run it, which can be useful if you want to. Then you can see if something does go wrong in the virtual circuit, you can see what you're doing wrong without frying a real live Arduino. So you can model a circuit in Tinkercad first, then replicate it in real life. You use Tinkercad to simulate things essentially. And once again, if something goes wrong in the Tinkercad, you just reset it. But if something were to go wrong with this physical Arduino, like if you fry a virtual Arduino, what's going to happen? You can just put it in it. You can just reset the simulation. Fry this actual Arduino, you're going to have to get a brand new one, and that's probably going to cost you like $20 or so. All right. Any questions? Feel free to speak up, guys. All right.
It doesn't look like it. We can kind of speed through a few of the previous parts, and then we can wrap up.
All right. So, a quick just review of the breadboards we've done. Like, the horizontal holes are linked together right here, but they do not cross the center divider. The vertical strips are linked along the length. Once again, don't cross the middle divider. And what some people do is they'll run a wire to both sides, and they'll run a wire between the two, so that the power rails and the ground rails are electrically linked by a wire. And another quick review of switches. As I mentioned before, a switch is a device that you can use to open or close the circuit at will. When the circuit is closed, the current can flow. When the circuit is open, there's a gap that can prevent the current from flowing through. We've used a button before, which is simply a switch that closes. When you press it down, the circuit is closed. When you release it, the circuit is open. This is simply a type of switch we've used before, and we'll probably continue using it. Next up, we have the LCD screen, or liquid crystal display. It's simply a type of screen that can display images by varying the brightness and color through a set of filters. The one we use is essentially a 7-segment display, well, glorified 7-segment display, but it can still display text pretty reliably. And LCD screens are extremely widespread. Like name pretty much any TV, computer, phone, what have you in your house, and I can almost guarantee that it will have an LCD screen. And then we go on to our good buddy, the servo, which is simply a type of motor that will allow precise rotation at a fixed interval. For example, 0 to 180 degrees. They're different from our traditional motors. They do not provide continuous rotation. Speaking of which, next workshop we will be getting into the more traditional motors, the ones that will allow more continuous rotation. And then something I just want to cover real quick is, I mentioned ammeters and voltmeters before. So an ammeter measures the current, voltmeter measures the potential difference. And then there's these devices called multimeters, like the one in this picture. I can perform both functions. You simply use the dial to select what function you want to use. And they have different settings. So you can determine, they have different settings so you can adjust how much precision you want. And an ammeter because an ammeter measures current, it has to be placed in series with the circuit. A voltmeter, meanwhile, it measures potential difference. So a voltmeter has to be placed in parallel. An ideal ammeter will have no resistance, and an ideal voltmeter will have infinite resistance. In practical terms, that's not usually the case. Ammeters always have some slight amount of resistance. Voltmeters won't have infinite resistance. Nothing has infinite resistance, actually. As isn't demonstrated by lightning. But those are the ideals, and those ideals are usually what are used in physics classes, for instance. And that's the end. Thank you guys for coming. Do you have any last questions? I can answer them.
Just a couple of reminders. So there'll be an email sent out after the workshop whenever I get around to editing the video, and that'll be sent out. The schedule should be in the email invitation for this workshop. These are planning to be weekly. We have a couple new people, so make sure that you have your embedded systems kit by next week. We'll actually be doing hands-on things. Otherwise, Stefan, did you have any other reminders?
No, I don't. Not off the top of my head, at least.
Right. If there are any questions now, you can always reach out to us through Discord. You can email, whatever. We'll get back to you. Otherwise, thank you all for coming. We'll see you next week.